So for lesson 113, we find ourselves here on GFCIs, AFCIs, and other special purpose receptacles. Notice that we do have to read EWR chapter 6 as well, which both books have some pretty good examples and illustrations here. What I put together here is kind of some examples and animations on GFIs and how they work. And what we're working with is basically the example that starts on page 113-4 here. So all the values I'm using come from this example. I did borrow some images and diagrams from the EWR book too, so I've kind of jammed them both together here, but they both have a lot of good to offer. So, so right off the bat, we got a lot of different parts of a GFI. I think it's a great time and a great excuse to just kind of examine how a normal circuit works, and we really have to understand that before we can understand how a GFI does what it does. But to begin with, right off the bat, we've got some different parts of the GFI. And these are all internal to the GFI. It's obviously exploded and enlarged here, but you don't really need to know every one of these parts and what they do, but we do want to just sort of have a general idea. So moving across, we have a shunt trip, so that basically that's the part, if this GFI trips, this contact is going to open. This shunt trip is what's going to allow that to happen. And again, this is a contact right now is closed, so the GFI is in kind of the reset position or the operational position. This is probably my favorite word in the whole book, but the toroidal coil. So really what you need to know are hot wire and neutral wire are ungrounded, and grounded conductor run through this coil. Really what all of the GFI does, it monitors current going out on the hot compared to the current coming back on the neutral. If it senses an imbalance amongst those two values, it'll trip. And we'll look at some animations explaining sort of why that happens and what that looks like. But that's kind of the key here, is this toroidal coil measures the balance of current between hot and neutral. If it's imbalanced, it trips. Okay. Solid state circuitry, again, you just need to know that's there, nothing really big there. Test switch, so you can kind of see if they push this switch, it'll sort of bypass our toroidal coil, which kind of gives us an imbalance. Again, you don't really need to know what that's all about, but and then in this diagram, this represents our receptacle, and then we have a 12 amp load plugged into that receptacle. So these are the parts we're working with here, so kind of keep that in mind. So this represents a normal circuit here, right? So you can see my electron flow here, and that's got a number 12 on for 12 amps. So if we were to put an amp clamp there, we'd see 12 amps going out through the ungrounded hot conductor. There's nowhere else for that current to go but back through the neutral conductor, so we see the same 12 amps going back through. Current's in balance, it's 12 amps on either conductor. So GFI is happy, it doesn't trip. And this is what happens on a normal circuit, whether we have a GFI or not. It doesn't matter. Obviously we're studying GFI, so we have the whole GFI set up here. And of course our ampacity is less than the breaker's rating, which in this case we can just agree is 20, so we're only 12 amps. Obviously a breaker's not going to trip either, so perfectly normal circuit, everything works the way it should. Now let's look here in this case where we may have a ground fault. So what that means is current is going to ground somewhere where it shouldn't, right? So we already looked at, we should just have kind of our normal flow of current. So we know it goes out through the hot, back through the neutral. We don't have any ground fault yet. But let's say there's a place somewhere here where that current doesn't follow this path back. That's going to represent a ground fault. So in this case, again, normal circuit still. 12 amps out, 12 amps back, everything's fine. Again, current's balanced. But now this guy comes in here, touches this, something energized here, and he's also grounded. So now what we've introduced is a alternate path to ground here. Because remember, all that current wants to do is go out through the hot, wants to get back to this point. Well, it just found another option to get back to that point. And remember, current's going to take all possible paths. Okay, this is a higher resistance path. It's got to go through his body. Maybe this water piping, it's the earth, whatever it is. It's higher resistance than just simply going like this. So he's not going to have the same amount of current. It's going to be relatively small, but he's still going to have some current flowing here. And remember, the human body is not a very good conductor, but it can't handle a lot of current either. So what happens here? Well, we still see our 12 amps going through the load like it used to, but we've also introduced this other path here. And if you look at the math they do, they calculate it to be 0.12 amps. It doesn't sound like a lot, but it is, enough to do some serious harm to the human body or some equipment. So So what we see here now, if we look, we're actually going to find 0.12 amps is going out through the hot, through our guy here, and through the alternate ground fault return path. So now we have 12.12 amps on the hot, but guess what? Only 12 amps is returning on the neutral. So now we have an imbalance going through this coil here. So that GFI is going to sense that, right? Current on the hot neutral is not balanced. Our contact is now going to open and actually kill power to the circuit. It's going to do that very quickly also. So this guy's still going to get a shock in this case, but it's going to be a very short time shock, okay? And the GFI is going to open. I believe your text is going to tell you if it senses a difference of 4 to 6 milliamps. In this case, we have 0.12, so we're above that range, right? So let's just look at the same thing without GFI protection now. So in this case, we just have our wires, our receptacle, our load. We've thrown the 20 amp circuit breaker in the mix for some illustration purposes. Again, receptacle, 20 amp load. So now the same scenario, but we don't have that GFI protection. Okay, so again, normal circuit, 12 amps out, 12 amps back on the neutral. No surprise there, right? We're less than 20 amps, so why would that breaker trip? Of course, it's not going to. Our guy comes in, gets in contact with something hot now. So we've introduced that same ground fault return path, so we have some leakage current here. But in this case, again, we have the same amount of current flowing everywhere. 12.12 amps going out on the hot, only 12 coming back. But without that GFI protection, there's nothing to measure that imbalance. The breaker is never going to trip, because remember, we only had 12 amps going out on this thing, right? So in this case, nothing trips, nothing interrupts that flow. Hopefully this guy can get out of that situation, but that's why GFIs, you see them in kitchens, in bathrooms, things like that. Truly can be some life-saving equipment here. So while we have all this up, this is somewhat unrelated to GFIs, but I want to look at what happens in a short circuit. So what would cause that breaker to trip, right? So the only thing that's going to ever cause a breaker to trip is if too much current flows through. So a short circuit means maybe we have hot to ground or hot to neutral with almost no resistance. Okay, so what happens there? Again, 20 amp breaker, receptacle, 20 amp load. We have our 12 amp flowing through, everything's fine. In this case, they're going to measure it again. In this case, maybe our hot wire went right up against the ground, or the metal grounded box, something like that. So that's a very low resistance short, as you're going to read about in your textbook. So in this case, and in their example, they actually calculate 1200 amps is going to flow. So you're going to have 1200 amps going through this ground fault return path. Okay, that's a heck of a lot of amperage for sure. So we're going to have over 1200 plus 12 amps in the hot. We're only going to have our 12 amps going back to neutral. That doesn't really matter. What does matter is that the breaker is overloaded by an extreme amount. That 20 amp breaker sees over 1200 amps, and it's going to trip almost immediately. So when we ground things, our intention is actually to allow an easy path for current to flow. The more current that flows and the quicker it flows, the quicker that breaker is going to open as well. You hear them called inverse time breakers. That's because what that means is the higher the overload, the shorter the amount of time it's going to trip it. So again, if you think about it, if we put 21 amps on a 20 amp breaker, it'll probably hold that for a couple of minutes. But the higher you get over that amperage rating, the faster that thing's going to trip. So in this case, on a short circuit, very low resistance short, there's very little resistance to current flow. A lot of current's going to flow. In that case, more amperage flows through the breaker, it's going to trip faster. Okay, so that's why it's so important to have such a good ground fault return path. So again, we there's a lot that we just went over there in about 10 minutes. Go through the examples and the diagrams in the textbook. This is a great way to sort of understand what we're looking at here, and the normal flow of current as well. So like I said, spend some time, really go through those examples, and spend some time thinking about this stuff.